Hello, and welcome to this introduction to calculus. Today, we'll be laying the groundwork for understanding how functions change, which is the core idea of calculus. Our journey begins with Chapter 1, Sets, Functions, Graphs, and Limits. By the end of this video, you will be able to define and represent sets, understand the concept of a universal set, and identify different types of number sets. These concepts are fundamental. Think of them as the alphabet of calculus. Mastering them will make the more advanced topics much clearer. Let's start with the most basic building block, a set. In mathematics, a set is simply a collection of objects. These objects can be anything: numbers, letters, people, or even other sets. There are two main ways to represent a set. The first is called set builder notation. We write S equals the set of all X, such that a statement about X is true. This is read as S is the set of all objects X which make the statement about X true. Let's look at an example. Imagine a company that wants to hire new employees. They might have a set of requirements. Let's define a set S as the set of all X, such that X is a person and X has a degree in computer science. This set S represents all the people who are qualified for the job based on this specific criterion. The second way to represent a set is by listing its elements. This is often used for sets with a finite number of objects. We can write S equals the set containing S1, S2, and so on, up to Sn. This notation simply lists all the members of the set. For instance, let's say a company has a set of 5 specific job titles they need to fill. We could define a set T as the set containing software engineer, data scientist, project manager, UX designer, and marketing specialist. This set T lists the exact positions the company is hiring for. So to recap, a set is a collection of objects, and we can describe it either by a rule using set builder notation or by listing its elements. Now let's talk about a special kind of set, the empty set. A set with no elements is called the empty set. It's denoted by the symbol you see on the screen, which looks like a 0 with a slash through it. Think of it this way. Imagine a company is looking for a candidate who is both a software engineer and a marketing specialist. It's highly unlikely they'll find someone with both skill sets. The set of candidates who are both software engineers and marketing specialists would be the empty set. It's a set that exists, but it contains no members. Next, let's introduce the concept of a universal set. The universal set, denoted by U, is a set of all possible elements from which the elements of any other set are chosen. It defines the context for our discussion. Let's go back to our company hiring example. If we're talking about the set of all software engineers, what would the universal set be? The universal set U could be the set of all people in the world. Or, if we're only considering people in a specific country, U could be the set of all people in that country. The universal set depends on the scope of our problem. In calculus, when we're dealing with numbers, the universal set is almost always the set of all real numbers. This includes all positive and negative numbers, fractions, and decimals. So, when you see a set defined like S equals the set of all X, such that X minus 4 is greater than 0, the universal set is implicitly understood to be the set of all real numbers. To summarize, the empty set has no elements, and the universal set defines the entire pool of elements we are considering. Now that we know what sets are, let's learn how to describe the relationship between an element and a set. We use the symbol that looks like a curved E to mean, belongs to, or is a member of. Let's use our company's job title set T. We can say that software engineer belongs to the set T. This is a true statement. What if we wanted to say that something is not in the set? We use the same symbol with a slash through it. This means does not belong to, or Anikira is not a member of. For example, is accountant a member of our set T? No, it's not. So we can write that accountant does not belong to the set T. This is also a true statement. This notation is a concise way to express whether an object is part of a collection or not. It's a fundamental tool for working with sets. Let's move on to a more advanced concept, bounded sets. A set of real numbers is said to be bounded above if there's a number, let's call it B, that is greater than or equal to every number in the set. This number B is called an upper bound. Imagine a company's stock price over a year. Let's say the price never went above $100. The set of all stock prices for that year is bounded above by 100. Any number greater than 100, like 101 or 200, is also an upper bound. The key is that there is at least one such number. Similarly, a set is bounded below if there's a number, let's call it L, that is less than or equal to every number in the set. This number L is a lower bound. Let's say the stock price never dropped below $50. The set of stock prices is bounded below by 50. Any number less than 50, like 49 or 0, is also a lower bound. A set that is bounded both above and below is simply called a bounded set. Our stock price example is a bounded set because it has both an upper and a lower bound. So a set is bounded if its values don't go off to infinity in either the positive or negative direction. Within the set of all possible upper bounds, there's a very special one. This is called the least upper bound, or LUB. It's the smallest of all the upper bounds. It's the tightest possible upper limit for the set. Let's go back to our stock price example. The set of prices was bounded above by 100, 101, 102, and so on. The least upper bound is 100. It's the smallest number that is still greater than or equal to every price in the set. Similarly, the greatest lower bound, or GLB, is the largest of all the lower bounds. It's the tightest possible lower limit. For our stock price example, the set of prices was bounded below by 50, 49, 48, and so on. The greatest lower bound is 50. It's the largest number that is still less than or equal to every price in the set. The concepts of LUB and GLB are crucial in calculus, especially when we talk about limits and continuity. They allow us to precisely define the edges of a set of numbers. Finally, let's review some of the most important sets of numbers you'll encounter in calculus. First, we have the natural numbers, denoted by n. These are the counting numbers, 1, 2, 3, and so on. They are bounded below by 1, but not bounded above. Next are the integers, denoted by z. This set includes all the natural numbers, their negative counterparts, and 0. The integers are not bounded above or below. Then we have the rational numbers, q. These are any numbers that can be expressed as a fraction p over q, where p and q are integers and q is not 0. Examples include 1/2, -3, and 0.75. The real numbers, r, are the set of all decimal numbers. This includes all rational numbers, plus irrational numbers like pi and the square root of 2. The real numbers are the universal set for most of calculus. Finally, we have the complex numbers, c. These are numbers of the form x plus I times y, where x and y are real numbers and I is the imaginary unit, defined as the square root of -1. While not the focus of introductory calculus, they are essential in higher mathematics. Understanding these number systems is crucial for defining the domain and range of functions, which we will explore in our next video. Let's quickly recap what we've learned today. We started by defining a set as a collection of objects and learned two ways to represent them: set builder notation and listing elements. We then discussed the empty set, which has no elements, and the universal set, which defines the context for our sets. We learned the notation for set membership, belongs to, and does not belong to. We explored bounded sets, which have upper and lower bounds, and the special concepts of the least upper bound and greatest lower bound. Finally, we reviewed the key number systems: natural numbers, integers, rational numbers, real numbers, and complex numbers. You are now able to define and represent sets, understand the concept of a universal set, and identify different types of number sets. These are the foundational concepts we'll build upon as we move into functions and limits. Thank you for watching.